So today, as part of the second module, we are going to learn about fast Fourier transform, and we have already learned about different kinds of transforms in the first module. And today we are going to start off with fast Fourier transform, which is an efficient way to compute DFT in a faster way by reducing the number of computations. As shown over here, this is the definition for a fast Fourier transform. It is an efficient way to compute DFT in a faster way by reducing the number of computations. I'll show you how the number of computations is reduced after doing the first example. It can be done in two techniques, decimation in time and decimation in frequency. The difference between the two methods will be clear when we do the problem. Radix 2 method is a concept that comes into play when we are learning about this particular topic, and when we speak about Radix 2 method, the signals will be processed in terms of powers of 2, where 2 raised to n samples would be there in a given signal, where n will be greater than or equal to 1. So typically, most probably you would be getting 4, 8, 16, 32 kind of signals when you do this particular problem, and our problems would be confined to 4 and 8, but you should be clear about how to do it if you are asked to give a theoretical explanation of how to do it for 16 or 32. But in practical scenarios, a particular sample signal can contain 1024 samples or greater than that. So the number of samples that we are doing right now is just for the learning purpose, but in practical scenarios the number of samples would be very high. Then we have to learn about twiddle factor, which we already discussed in transformation property of DFT, and we learned about WNK, and if we have a concept like WNK, it can be replaced as e raised to minus j 2 pi k by capital N. So this is an explanation for twiddle factor or WNK, which is something that we use over here. And moving ahead, we are starting off with the decimation in time method. So proceeding with this method, we have to get an understanding of the steps, which I have written over here. I'll give you an explanation for a case where we are going to do it for a particular case of 4-point signals. So and we'll see for 8-point also while we explain it over here. So the first step would be determine n, which is the total number of inputs, which as mentioned will be in powers of 2, either 4, 8 or 16. So if it is 4-point system, then it will be n equal to 4, and here n will be equal to 8. The second step is determine m, which is the number of stages required. So we are having some stages of operation to be performed over here, so that can be determined as m. And based on our equation given there, we have 2 raised to m is equal to capital N. So here 2 raised to m will be equal to 4, which means m will be equal to 2, and here m will be equal to 3. That means for 4-point DFT there will be 2 stages, and for 3-point DFT there will be 8-point DFT there will be 3 stages. I repeat, for 4-point DFT there will be 2 stages, and for 8-point DFT there will be 3 stages. The next concept is of a butterfly diagram, which is something that I have mentioned over here. It is basically representing an operation that is performed between 2 signals. So if A is a signal over here and B is a signal over here, as you see over here, A is available here and B is available here, we are having a diagrammatic operation of this particular signal being done over here. You have a multiplication factor of WNK, which is available here, the twiddle factor that we had mentioned before. It is placed at this point. Please note that the position of the twiddle factor and this multiplication factor of -1 is important. So if you look at me, the signal on this arm is A at this point and the signal on this arm is B at this point. Let us evaluate them at different points. So at this point, what would be the signal? It will still be A, and at this point also it will still be A. At this point, till this combining point, this point it will be A. But as soon as the signal B flows here, it is multiplied with WNK. So the signal at this point will be BWNK. Now that BWNK flows in this pattern, and here it will be summed up. So here you have A and here you have B, BWNK. So together it will be summed up and you will be getting as A plus BWNK. Now, if you look at this arm, we need to see what is the signal at this arm. So we have a component coming here, that is A. Now we have to identify which is the component coming here. So up to here it is B. Here it will be B, W and K, and that will be multiplied with -1. So you have minus B, W and K. And together when you combine it, it becomes A minus B, W and K. I hope this concept of a butterfly is also clear. So kindly note, you have this, all elements are important. You need not draw these arrows, but otherwise you have to draw A, B, W and K and -1. The position of W and K is important, and once it changes, the entire butterfly diagram logic differs. So you need to get a concept of this butterfly diagram for this particular problem. Then the order of the stages is of concern, and here you can say that your order of the stages will be defined in this manner. So starting off, at the end, right end, you will be having n point DFT. Before that you will be having n by 2 point DFT. Before that you will be having n by 4 point DFT and n by 8 point DFT and things like that. This n point DFT will be done 2 raised to 0 times. This n by 2 point DFT will be done 2 raised to 1 times. This will be done 2 raised to 2 times, and that is a logic. So let us evaluate how it will happen for a 4 point DFT. For 4 point DFT, how many stages are there? 2 stages. And what will be the 2 stages? Starting from the last, you will have n point DFT. So that will be a 4 point DFT. And before that you will have n by 2 point DFT. Now n is 4 here. So you will be having 2 stages. So the last stage is 4 point DFT, and before that you will have 2 point DFT. And there won't be any other stages prior to this. Only 2 stages will be there, and the last one will and the first one will be 2 point DFT. And this will be done 1 time, and this will be done 2 times. Let us look at for 8 point DFT. Now when you point about n point DFT, n is 8, so which means m will be equal to 3, and which means there will be 3 stages, 1, 2 and 3. So the last stage here will be 8 point DFT. This will be 4 point DFT, n by 2. So it will be 4 point DFT, and this will be 2 point DFT. So that makes up the 3 stages. This will be done 1 time. That is 2 raised to 0 equal to 1 time. This will be done 2 raised to 1 times, which will be equal to 2. And this will be done 2 raised to 2 times 4 times. 2 raised to 2 equal to 4 times it will be performed. I'll give you an idea about what it is when we move ahead with the program. So that was it about the order of the stages. Then we come about with the twiddle factor for each stage. Now, we know about what are the different kind of stages involved. For an endpoint stage, we'll need twiddle factors from Wn0 to Wn n by 2 minus 1. So for a 4 point DFT, you'll be having 2 stages, and for the 2 stages, the 2 stages are the 2 point DFT and 4 point DFT, which we have already seen earlier, and which will be done 1 time and 2 times. It is already mentioned here. So the twiddle factors required for 2 point DFT will be computed as based on this format. So it will be required from W20 to W2, n is 2, 2 by 2 is 1, 1 minus 1 is 0. So the only twiddle factor required for a 2 point DFT is W20. And the twiddle factor required for a 4 point DFT will be W40 to W41. I repeat, W40, n is 4, so it will be W40, and W4, when it is 4, 4 by 2 is 2, 2 minus 1 is 1, W41. So you require 2 twiddle factors, that is W40 and W41. So we are going to compute it. W20, as you already know, it is e raised to minus j 2 pi into 0 by 2, which makes it e raised to 0 equal to 1. So that is already mentioned here. Similarly, W40 will also be 1, and W41 will be e raised to minus j 2 pi into 1 by 4, which makes it e raised to minus j pi by 2, which makes it cos pi by 2 minus I sin pi by 2 equal to minus I. The last topic that you need to focus on this steps would be to write the input in the bit reversed order. So to write the input in the bit reversed order, the concept is explained as below. If n is equal to 4, which is here, your n is equal to 4. Now, which means the input samples will be containing x of 0, x of 1, x of 2 and x of 3. 4 elements will be there in the signal, and if we are assuming our x of n is 3, 5, 7, 9 as the input sample space. So your table can be written over here. X of 0 is 3, x of 1 is 5, x of 2 is 7 and x of 3 is 9. This is input in the normal order. Please understand that. This is the input in the normal order. So we identify the positions. What are the positions or the value of n? 0, 1, 2 and 3. So we write the binary versions of that. For 0 it is 0, 0. For 1 it is 0, 1. For 2 it is 1, 0. And for 3 it is 1, 1. And its bit reversed order will be as follows. We reverse the bits. So 0, 0 it is 0, 0. For 0, 1 it will be 1, 0. For 1, 0 it will be 0, 1. And for 1, 1 it will be still 1, 1. So this will be x of 0. This will correspond to x of 2. This will correspond to x of 1. And this will correspond to x of 3. So the bit reversed order of a signal will be x of 0, x of 2, x of 1 and x of 3, which means it is 3, 7, 5, 9. So our normal order of the signal was 3, 5, 7, 9, and the bit reversed order of the signal is 3, 7, 5, 9. Please note that the reversal is happening with respect to the position, not the values. And why did I limit this to 2? Because the highest value of 3 requires only 2 bits. If it was an 8-bit system, it would require 3 bits, and for a 16 it would require 4 bits. We'll look into that in the later sections on the problem. I hope the method is clear, and we'll start doing the problem in the next video.